Hello everyone, my name is Alex Mostovoy and I will be reviewing this paper titled Visual Surveying Spanner Picking and Placement with a SCARA Manipulator. This paper talks about a robotic arm which aims to replace manpower in some handicraft tasks. One of the main concepts behind this robotic arm is the visual surveying application. It is based on a computer algorithm that enables the detection of objects and calculation of their position and orientation within the workspace. So you have a camera mounted here on top of a table and a motion controller underneath it, and then a robotic SCARA arm on the side. In the vision field of the camera, 4 sensors are placed on the corners, so you have this vision field outlined in yellow, and 4 sensors are placed on the corners, which defines the workspace. And to better illustrate how this model looks, I made a CAD model of it. So as you can see, it has 2 arms, one red and one blue, and 4 motors. They are colored in black. The plane you see here, this plane is the workspace, and the green is the field of view of the camera. So we have a camera somewhere here on top, and the green is the field of view of the camera. This is motor number 1, which is responsible for the movement of this blue arm for rotational movement. It is limited to 300 degrees, so it can perform like this motion up to 300 degrees. And then the second motor is responsible for the rotational movement of the red arm, again 300 degrees, like this. And then we have motor number 3, which is responsible for the translational motion of the robotic claw, up and down, like this. And then finally we have motor number 4, which is responsible for the rotational movement of the claw, so the claw can rotate like this. That is the setup and the workspace. If we look from the top, the workspace is defined by this arc right here, and of course by the field of view of the camera. So it would have this shape where it's like an arc, and then you have the corners cut off. And that is the workspace. Inside of this, the robot can operate. It can reach any, as you can see, it can reach any point within this workspace, and the camera covers all of it as well. So what I showed in the CAD model, you can also see here in figures 2, 3, 4, and 5. For example, figure 3, you have the top view, and you can see this arc, which limits the workspace of the robot, and also the yellow camera field of view, which is approximately 500 millimeters by 730 millimeters. The robot has 2 arms, and both of these arms are 250 millimeters long. Belt pulleys and gears are used in this design. The belt pulleys provide better flexibility and smoother transition between the motors and the gears. And the gears have ratios optimized for the loads they have to deal with. So we can notice how the third gear has a ratio of 1:1, and that has to do with the fact that it's the only motor responsible for translational motion. As we can see in figure 4, motor 3 is responsible for the translational motion of the robotic claw. And motors 1 and 2, on the other hand, have to also move the weight of other components of the robot. For example, motor 1 has to move this arm, and it also has to apply enough torque to be able to move this other arm and the claw and all other motors, all these other components, and not only the load. And this is why the gear ratio for motor number 1 is the largest, and then we have a smaller gear ratio for motor number 2, because motor number 2 doesn't have to apply as much torque, because motor number 2 is not worried about moving this blue arm. So motor number 2 has a smaller load compared to motor number 1. And then finally, motor number 4 has the smallest load because it only constitutes of this claw and anything that the claw picks up. With regards to the kinematics analysis, this is our DH table right here. Theta 1 and theta 2 are both 300 degrees, and L is 250 millimeters, because L is, again, these two arms have the same length. So this is our first transformation matrix, our second transformation matrix, and this is the final one. And for the inverse kinematics, we have this Cartesian space right here, which is basically a top view of the robot. So this is our top view, and this is basically our Cartesian space for the inverse kinematics. Now for these angles, the theta angles, here's how they were derived. For example, let's look at formula number 6 right here. We have a law called law of cosines that states, for example, for any triangle, cosine of alpha would be equal to this. Now, if we apply it to this triangle right here, here's what the law of cosines would look like. Cosine of theta 2 prime would be equal to this. L2 squared plus L2 squared minus b squared, right? And then we divide this whole thing by 2l squared. So 2 times L, which is equal, if we transform this, and if we substitute, instead of b, we substitute x squared plus y squared square root, we would get 2l squared minus x squared minus y squared over 2l squared. Therefore, since theta 2 is equal to pi, which is 180 degrees, minus theta 2 prime, right? We have theta 2 is equal to pi minus inverse cosine of this expression, which is theta 2. And if we look at the paper, it's exactly the same formula right here. So this is how the formulas for the inverse kinematics were derived. Formula 6 I just showed. Same goes for formula number 5 and sigma. If we look at the diagram, sigma is right here, and it's also this angle right here. So we have this triangle, which is a 90-degree triangle here, right? And this angle is 90 degrees. So the tangent of sigma would be the opposite over adjacent, so it's y over x. And this is why, if we look at the formula, sigma is tangent inverse y over x. And theta, equation 5, is this big expression minus this. And again, if we look here, tan inverse y over x is sigma, so theta is, as it turns out, theta is this angle right here. Theta is equal to this large angle minus sigma, right? And if we look at the formula, we have this expression for this large angle, which can be obtained using the law of cosines for this angle, just like with formula number 6, which I just showed. We can apply the same law of cosines to this angle right here and get this expression. And then we subtract sigma, which is inverse tan y over x. So we subtract this angle, and we're left with theta. So as I mentioned before, this robot uses a camera that has a rectangular field of view, and the camera uses a Harris corner detection algorithm, which enables the corner points of the image to be found automatically. So this is how it works. We have an edge, which means a sudden change in image brightness, and a corner can be viewed as a junction of two edges. So we assume a two-dimensional image is used, and we let I be the image intensity gradient. So we have Ix and Iy respectively. And let's say we take an image patch xy, some arbitrary xy, and we shift it by delta x and delta y. The sum of square differences, the SSD, denoted by f, can be found using the following formula, and we can approximate this term underlined in red using the first order Taylor expansion approximation. We can rearrange the SSD into matrix form as shown here and obtain the final result, which is shown in the article right here, formula 8. So this is a gradient information matrix H. Now the Harris response matrix R is calculated in equation 9. Its determinant of H minus K coefficient set to 0.6 times the trace of H squared. K is an empirically determined parameter, so for this robot it's 0.06. Then we have the image warped by equation 10 for final calibration. And this means that the image is made to fit into a frame of desired shape. So we have this frame right here in green, and that is our desired shape. The overall procedure for image calibration is shown in figure 8 right here. So we go from the input frame to converting to gray image, black and white, to Harris corner detection algorithm, then we convert it. Binarization means black and white image, as we can see here, or for example later, right here. And then we have morphology, meaning we study the shape, and the result would be the corners that are detected. So we get those 4 corners and we transform them, warp perspective, and as a result we get this improved image. So we went from this figure 9 to figure 11. And then next step would be selecting a region of interest, ROI, that's figure 12. We have ROI on the left as these randomly placed spanners, and then we have a toolbox on the right, and our goal, our objective would be picking up these randomly placed spanners and moving them to the toolbox and aligning them with other spanners. After that, the green background is removed, allowing us to get information such as the location of the spanners and their surface area. That's figure 13. Then the region of interest is changed to further analyze the spanners, primarily to detect their slopes, and we can see this in figure 14, where these small red rectangles are the new regions of interest. And for this task we use a canny edge detector to locate the spanner's edges. This method is shown in figure 15, and it uses a Gaussian filter to smooth the image and then compute the edges. And there's another referenced paper on this, and this is basically what it looks like. It uses this formula and it takes the original color image and filters it for analysis, and then this is called the Gauss filter, and it's outlined in this paper. So then, as we need to find the slope, we use a Who transform method to find the lines from the edges. As we can see in figure 16, we need to find this red line, which is a slope. And because we know the coordinates of the line's start point and end point, we can obtain the slope of the spanners. And the Who transform method, this is another article that's being referenced in the paper. Basically, it establishes a relationship between a line L and the angle theta and distance rho from the origin to that line. So it's a simple formula, and even though the algorithm is improved, but this is the basic principle, and as we can see, it works pretty well. We have a noisy image, and at the end we have clear and straight lines. And finally, as the last step in image processing procedure, we have transformation of coordinates. So a conversion is done from pixels to millimeters, which is shown in equation 11 right here. We are converting Ix and Iy to Rx and Ry respectively. So 735 is the robot's view range, and 588 is the height of the image. 500 is the view range, and 400 is the image width. So this is a conversion matrix. So figure 18 right here outlines the entire procedure, with the green region being the analytical procedure, image processing, and the red region being the iterative movement of the robot, and depending on how many spanners have to be moved, this can repeat several times. And for the experimental analysis, we look at table 3 right here, and what is interesting is that we have the largest errors in terms of length for the smallest object, and I assume that has to do with the fact that smaller objects are harder to detect and analyze due to relatively low camera quality. So we have the largest margin of error for the smallest object, which is only 126 millimeters, and we have the relatively small margin of error on the largest object, object 5. So in the paper, this design is proposed for industrial manufacturing, with low cost and high capacity listed as advantages. There are some practical problems, and one of them is mentioned: overlapping spanners. A solution to that would be a depth sensor, infrared or ultrasonic, that would keep track of height difference. Also, I would like to point out a few other problems. For example, picking up spanners, just like here, doesn't seem like a real-world scenario to me. I mean, you could do it, but what would be the application where we have spanners or other instruments just laying randomly on the ground like this? I was thinking about possible applications, and I could not think of any super solid potential real-life application for this design. So since this design only uses one claw, it can be very hard to pick something up having only one point of contact. So this claw, even though it is using the center of the object as a contact point, some objects can be, pretty hard to grab, and as a result, they could fall from the claw. To conclude, I agree with the authors that this is a cheap and effective design, but the application of this robot has many constraints which limit its practicality. There has to be a camera mounted on top, there has to be a flat surface on which the robot can operate, and the objects have to be solid and of such shape that they can be picked up with only one claw. That is all I have. Thank you for your attention.